Welcome to my talk on manifolds in Julia. And first of all, let me thank the organizers, both for organizing the JuliaCon, as well as giving me the opportunity to give a talk here. This is joint work with Seth Axon and Mateusz Baran. Seth is from the University of California in San Francisco, and Mateusz is from the AGH University of Science and Technology in Krakow in Poland. And I'm from the University of Chemnitz in Germany. So when we want to work with manifolds, the question is, why do we want to do that? And the simplest example is cyclic data. So you measure an angle, for example, over time. Let's say in a second you take 1,000 measurements, like on the right. And the original data might have been the gray value at top, this one. But you measure it modulo a wavelength, for example. So it gets wrapped on the circle, and you end up with the black signal below. But the jump you see is not a jump. It's a continuation that's wrapped around the circle. But it might even be worse when your data is noisy and you look at these 2 points atop here. Then classical methods cannot reconstruct the original signal, and you have to take into account in all your processing that the data is cyclic, so it lives on the circle. Another example is the sphere. So if you want to model a curve on the sphere, for example, you have to make sure to not leave the unit vectors that make up the sphere. So your data has to stay on the sphere to be valid, for example. Another example are orientations. So you have an orientation of an object and ask yourself, if I move it to this orientation, how far is that away? So you want to have a way of measuring distances between orientations. The fourth and last example are diffusion tensors. So you want to measure diffusivity in a certain material. And you can represent that by symmetric positive definite matrices. That is, they model an ellipsoid. And the larger directions kind of like block diffusion more, and the smaller ones allow for more diffusivity. And then you end up with an image like the one on the right, where each point is exactly such a diffusion tensor. And for all of these, you cannot just add 2 points, so it's a nonlinear space. And they have enough structure to be a Riemannian manifold. And that's what we want to tackle with the packages and in this talk. So we want to transfer properties, methods, and whatever you want to provide to manifolds. And I want to talk about statistics today, for example, of data processing and imaging, and in the end about optimization that are implemented for any manifold. And we also provide a library of manifolds to then easily use this manifold or that manifold that fits your data. And want to do that, of course, with multiple dispatch. So a small step back to the background. What's the Riemannian manifold? It's a set that locally looks like RD, usually described by charts. Imagine the sphere and your atlas at home to map certain areas onto a sheet of paper. Then locally, the Earth always looks flat, like R2. But globally, it is not. And another way we need is we have to be able to measure angles or have a norm locally. And that's what the inner product is for. And it has to be very smoothly with P. That's a little technical, but we need a point, at any point, the possibility to measure angles and locally something like distances. We will see that in a minute. So a few more terms. The geodesic is the shortest path between 2 points. So between P and Q, we have the connecting curve of shortest length that's called geodesic. At a point P, we have the tangent space. That's a local linearization of the manifold. And in there, we need this inner product I just talked about to measure angles and induce a norm, for example, of this tangent vector x that points into some direction that you can see in the image. And two further quite important functions are the logarithmic map. So given 2 points, which direction do I have to go into to get there? So for P and Q, that would be the vector x. And the inverse is, I'm at P and I'm given a direction x with this length. And the question is, where do I end up? That's the exponential map. And while the exponential map usually for complete manifolds is defined globally, the logarithmic map is only defined locally. The example is the North Pole on the sphere, and you ask yourself, how do I get to the South Pole? There's no unique answer. You can take any way as long as you walk half around the Earth. Then you have the South Pole. So the logarithmic map might only be defined locally. It corresponds to minus for the Euclidean case, and the exponential map is plus, and geodesics are straight lines in Euclidean space. But here we are more general. With these, let's get into implementations. So in Manifolds.jl, a manifold is a subtype of the manifold type. That's again parameterized by the field, real, complex, or quaternion valued. We only work with the real valued during this talk. And then the ManifoldsBase.jl has a set of functions that you can implement for a manifold, inner, exp, and log that we just discussed. Or more general, the retraction, which approximates the exponential map, first order or second order approximation, or even the vector transport that identifies vectors from different tangent spaces with different transport methods T available. One further tool we provide is the mutating versions, so that you don't have to reallocate memory when you know that your result should be stored in Q anyways. Then the second argument is always the one you want to mutate for the results, so for exp and log, for example, or for the retraction. And if you implement these, you could already get a few tools for free. For example, the norm, if you implement inner, the geodesic, if you implement exp and log. And here note that that's the geodesic, so it might be any curve you follow that is locally shortest, but globally, if you start in P and walk into direction x on the sphere, you might end up walking once around the sphere. So that's why it's called geodesic, and we compare that to the shortest geodesic, which is just really the shortest connection between P and Q that you would walk along then. That's great arcs on the sphere, but they are already implemented if you provide the tools atop. In general, a lot of things like the inner products, the Riemannian metric tensor, are implicitly assumed. So for the sphere, I did not talk about it, but I just said great arcs for the connection. So with that in mind, we implemented a decorator pattern that acts semi-transparently for all functions that you want to have, so you can always activate or deactivate transparency. For example, the manifold dimension will for most cases be transparent. For example, for the validation manifold, that when applicable adds is manifold point for points you plug in or you get out of a computation, or checks whether it is a tangent vector that you get out, that x is actually a tangent vector on that manifold. And that can just be added around any manifold to add further testing when you're developing. I want to show 3 further decorators in the following. The first one I already mentioned is the different metric. So we want to do a metric manifold that has both a manifold now as a set of points with these charts in mind, though we don't want to store the charts, and the metric that induces how to measure angles. For the first one, you don't have to think about this. So the symmetric positive definite manifold has just the linear affine metric implicitly assumed, and the metric manifold acts then transparent for those. And the other two ones, the log Euclidean and the log Cholesky, you have to implement it with this type to implement those functions. So for example, the log Cholesky provides an exponential map, and the other one just provides a tensor, and that means there's no closed form for the exponential map, and we then try to solve it numerically, solving the corresponding ODE. Another decorator are embedded manifolds. So that's the idea of reusing methods that are defined on larger spaces where you can embed your manifold. The sphere S2 can very easily be embedded, or is even represented for most cases, in R3 as unit vectors. So then we want to maybe reuse the inner product and switch between those points or representations by calling embed or project, or even look at the manifold we embed into by saying get embedding. And the first example is exactly the sphere, where the default isometric embedding says please use the inner product from the embedding. Then we don't have to implement that for the sphere if we phrase it this way. Another example are the symmetric matrices that are also a manifold, embedded in the Euclidean space of n by n matrices, but they can even reuse expand log. That's why the transparent isometric embedding even goes a step further. We just have one implementation on the Euclidean space for expand log and don't have to re-implement that. Or you can just say this manifold is embedded in this embedding and provide embed, project, and get embedding to switch between the representations of the points on the manifold compared to the embedding. And as a last example, the Lie groups extend Riemannian manifolds to the case where you additionally have a group structure. So we have a binary operator that acts on the manifold and returns points on the manifold. We always provide the identity element, and then together with the metric manifold you can also specify whether it's left, right, or B invariant, which is already a little bit technical. Let's look at a few examples. The translation group is the Euclidean space with translation, so addition. Then we have the special orthogonal group, that's rotation matrices. So as set or manifold, it would just be rotation matrices. But together with the multiplication operation, we get a Lie group because two rotations concatenated, so doing both rotations, gives you in total again a rotation. And the special Euclidean is the semi-direct product group of these two, so the special orthogonal and the translation group. And you can also do that yourself again, saying I want to have the group manifold of this manifold and that operation that then accepts 2 points on the manifold and returns the result of the group operation. If we want to build more manifolds, then the product manifold takes a set of manifolds and has an entry for every manifold point. So we get a tuple that lives then on the product manifold. And you can easily construct them by just saying M1 times M2 in Julia. And we also provide an easy way to store these tuples of points, because it might be a vector and a matrix and another matrix. So we have to find a good way to represent those. The next one is the power manifold. So you have one manifold and take the product with itself. Then you can also use m to the power 5, 6 to get the power manifold. And then you have either arrays or nested arrays, depending on what you prefer, to represent points on the power manifold. The next one we automatically build is the tangent bundle. That is, the manifold and the collection of the tangent spaces also form a manifold. So that's n is the tangent bundle of n. Or more general, we also provide vector bundle fibers. And we implemented an easy way to access the elements for product and power manifolds. So with array access and the first element set to a manifold, you can easily access the ith element on the power manifold or product manifold if P is such a point. Let's get into an application. So for statistics, one important thing to compute is the mean. As I already said, we cannot just add points on a manifold. So this one cannot be done directly on a manifold, but we can rephrase it because this 1 over n and the sum of points is the minimizer of the distance squared between the points xi and some y. So we can rephrase that to use the distance. So on a manifold, that's the minimizer from the points to some y, and we get a optimization problem that's even smooth. There's in general no closed form for this, but if we have a tool to compute this minimizer, we can at least numerically approximate it. And it's called the Riemannian center of mass. Here's the method for that. So just calling mean of x with weights in the method. You can even compute the weighted mean with one of the methods we provide, the geodesic interpolation or the gradient descent, or maybe using an extrinsic estimator, again in the embedding. With the mean available, you can compute the variance or a lot of other tools from statistics that we transferred to manifolds in this generic sense. Another possibility that is also derived in the same manner is the median, which is a minimizer of the distances to one point y. This is a non-smooth optimization problem, and we provide the cyclic proximate point estimation for that, which goes back to Miroslav Baczak a few years ago. The next idea is, if you actually want to go to tangent vectors and represent them as d-dimensional objects, which in general is not the intention of the representation, you need a basis of the tangent space to then use the inner product to decompose your vector into coordinates. And maybe you even want to use a few more things of your basis. So like, for example, the diagonalizing orthonormal basis even takes into account the curvature of the manifold. So diagonalizes the curvature tensor, which might be handy for some computations. And we don't store the basis explicitly, but provide an iterator. If you want to have it explicitly, you can use the cached basis. Then you directly get the complete set of vectors that form the basis. And with that, you can call get coordinates to reduce it to a d-dimensional array. And you can reconstruct the vector by calling get vector with the corresponding basis. And that also works for the non-cached ones, right? So then we're going through the iterator and reconstruct the vector from that. Okay. The manifolds available are here marked in color for the complex valued ones. For example, the circle can be represented as angles, minus pi to pi. We saw that on the first slide, but also as complex numbers of norm 1. That's the circle in the complex plane. And for example, the Euclidean space is even available for quaternions and can of course be used quite high dimension. So to do any comparisons in the algorithms, you can always also use the Euclidean space ones to compare to classical linear spaces as a comparison. Further manifolds are the Grassmann manifold, for example, or the hyperbolic space. or the manifold of rotations we saw in the beginning. And last one in the list is, for example, or the third to last one is symmetric positive definite matrices, or the sphere that even works for unit norm arrays. So then you have to take the Frobenius norm, of course, but also for the complex valued case, we have that available. And maybe also your favorite manifold. So with that, let's get into another application. If we want to do a PCA on the sphere S2, so we have a set of points shown on the right, and we want to have the main axis or the main variation direction of this data. So then we are facing a problem in multivariate statistics, but on the manifold sphere too. So that's the first things we need. And then we can compute the mean. That's the orange point over here, over there. And from that we can take the logs to kind of like pull all the points up into the manifold, into the tangent space at the mean. I didn't draw all of them, but you see most of them mapped. And then we decompose every tangent vector into its coordinates with respect to this orthonormal basis in the mean tangent space, and get a two-dimensional representation of all these logs, which would be usually stored as vectors in R3. But from that on, we can do the model fitting of a PCA and just get the main dimension out, that's max out dim 1, and reconstruct the vector x that's shown in the image on the right. And to get a better image of this, we can then take the geodesic from -1 to 1 to draw the main axis of the PCA on the sphere, which is then this orange line. And if I now want to switch to another manifold, I just have to have, well, other points and change the second line of the code. All the rest works generically on any manifold that provides mean and log. Let's get into an application that I'm interested in and build upon the manifold space. That is, I want to minimize the function f over a manifold, where the problem P stores the function, maybe a gradient, maybe a Hessian, and with the options I specify which solver to use and the current state of the solver. Then calling solve within Manifolds.jl, I can solve this problem. And we also provide a lot of stopping criteria to specify when to stop. And a solver usually consists of two functions, initializing the solver and doing one solver step. And this all falls into the regime of manopt, which started in MATLAB, manopt.org, and is also available on PyManopt, and now also based on the framework just presented in Julia. Let's look at an example. Oh, we first need the solvers. One is gradient descent. The cyclic proximal point we already saw for the median. And you can, of course, also do something like Nalda meet or Riemannian interest regions. And an example looks like this. So if I take the sum of distances squared of the points to some y and specify the corresponding gradient, then I can easily do the gradient descent for that and compute the mean, even with some debug output or similarly with some record. Okay, let's summarize. So ManifoldsBase gives us a flexible and lightweight interface for manifolds. Manifolds, on the other hand, provides a library of basic manifolds and ways to extend them, provide group manifolds using the decorator pattern. Manifolds.jl is built upon that and gives us a way to do optimization on manifolds, but on all manifolds that are implemented within Manifolds.jl. And our next steps are automatic differentiation, for example with Zygote, a generic way to implement distributions, and we want to do more abstract manifolds, so quotient manifolds, projective spaces, and also more manifolds. So if you're missing a manifold, get in touch with us and we can see what we can do for your favorite manifold. And with that, here's a little bit of literature I mentioned during the talk, and the 2 URLs. You can look into the documentation of the packages. And with that, thank you for your attention.